So the next topic is grain size analysis. This is also known as mechanical analysis or particle size analysis. So this particle size analysis or grain size analysis is a method of separation of soils into different fractions based on particle size. That is, based on particle size we are separating the soils into different fractions. So that process is known as grain size analysis. Okay. It expresses quantitatively the proportions by weight of various sizes of particle present in the soil. So we are classifying or categorizing the soils based on sizes into different fractions by weight. Okay, and after that it is shown graphically on a grain size distribution curve. So this grain size distribution curve is very important. So this grain size distribution curve is actually the graphical representation of grain size analysis. That is, the grain size analysis, the result of grain size analysis is graphically represented using grain size distribution curve. Okay. So this grain size analysis is usually performed in two stages. First is sieve analysis, second is sedimentation analysis. So the sieve analysis is usually done for coarse grained soils. That is, coarse grained soil means the soils with size greater than 75 micron, okay, or 0.07075 mm. Okay, that is coarse grained soil. So for this coarse grained soil we are doing sieve analysis, and for fine grained soil, that is the soil with size less than 75 micron, we are usually doing sedimentation analysis or wet mechanical analysis for fine grained soil. Okay, that is, this grain size analysis is done by sieve analysis for coarse grained soil and by using sedimentation analysis for fine grained soil. So first we can discuss about sieve analysis. So in the sieve analysis, the soils are sieved through different set of sieves. Okay, so this is known as sieve. This is one sieve. There is a set of sieves, and these sieves are wire screens having square openings. Okay, so this is a sieve. So as per IS, the sieve number is the mesh width expressed in mm of larger sizes and in microns for small sizes. So based on this mesh size, we are expressing the sieve size also. Okay, sieve number. Sieve number is the mesh width. Actually, for this sieve, if the sieve number is 4.75 means this mesh width will be 4.75 mm. Okay, so sieve number is the mesh width expressed in mm for larger sizes and in microns. For some sieves it will be expressed in micron. For example, if the sieve is 75 micron means this mesh size will be 75 micron. Okay, so that is the meaning of sieve number. And the sizes greater than 4.75 mm is called gravel fraction. That we have studied here. That is, size greater than 4.75 mm is known as gravel fraction, and size less than 4.75 mm is known as sand fraction. Okay. So here also, for size greater than 4.75 mm is called gravel fraction, and a set of coarse sizes consisting of the sieves of size 80 mm, 40 mm, 20 mm, 10 mm and 4.75 mm are used for gravel fraction. Okay, so for gravel fraction, the sieves will be having size greater than 4.75. So greater than 4.75 means there will be 4.75 mm sieve, 10 mm sieve, 20 mm sieve, 40 mm sieve and 80 mm sieve for sieve analysis of gravel fraction. Okay, and for sand fraction, sand means the size between 4.75 mm and 75 micron. Okay, that is, sand means size between 4.75 mm and 75 micron. So the sieves will be like that. That is, it will be 75 micron, then 150 micron, 212 micron, 425 micron, 600 micron, 1 mm, 2 mm up to 4.7, that is less than 4.75 mm. Okay, so these values should be by hearted, and here it is arranged like this. This is for sand fraction. Okay, that is, sand fraction means between 4.75, that is less than, size less than 4.75 mm. Okay, so 4.75 mm less than 4.75 means the next size is 2 mm, 1 mm, 600 micron, 425 micron, 212 micron, 150 micron, 75 micron, and below that there will be pan. There will be a pan for collecting the residue which is passing 75 micron. So this is the arrangement of sieves for sand fraction. Okay, So this sieve analysis may be dry sieve analysis and wet sieve analysis. So this dry sieve analysis is suitable for coastal soil with little or no fines, and here for dry sieve analysis usually oven dried soils are used without any water content. Okay, and it should not contain any lumps. If necessary, it should be pulverized. There should not be any lumps, and gravel fraction and sand fraction is sieved through the corresponding sets of sieve. So this is the set of sieves for sand fraction. Okay, and for gravel fraction, the set will be 80 mm, and below that 40 mm, 20 mm, 10 mm, and 4.75 mm. That is for gravel, and this is the arrangement for sand fraction. Okay, that is various sieves arranged one over the other with a pan at bottom and a lid at the top. Okay, lid at top, and the sieving may be done manually or using a mechanical shake. Okay, either we can sieve by manual method, or we can put it in a machine, and using mechanical shaker we can sieve for around 10 minutes. Okay, and after that, after sieving mechanically or manually, the weight of the soil which is retained on each of the sieve is obtained. Okay, that is after sieving, after mechanical sieving, there will be soil fraction which is retained on each of these sieves. So the weight of the soil which is retained on each sieve is calculated. Okay, and next is wet sieve analysis. So here it is recommended if the soil contains substantial quantity of fine particle. If there is more fine particle, we have to go for wet sieve analysis. The dried sample is taken in a tray and soaked with water, and 2 grams of sodium hexametaphosphate is added per liter of water used for deflocculation, and sample is stirred and left for a soaking period at least for 1 hour. Okay, and this slurry is sieved through 4.75 mm IS sieve and washed with a jet of water until wash water becomes clear. Okay, then material retained on the sieve is if the material which is retaining this 4.75 means it will be gravel fraction. Okay, that is the size greater than 4.75, and the material which is passing 4.75 sieve means it will be fine. Okay, so and it is sieved through 75 micron sieve, and material retained on 75 micron, that is which is passing 4.75 and retaining on 75 micron is sand fraction. Okay, and the coarse fraction is dried in an oven and dry sieve analysis done. And for fine fraction which is passing 75 micron, we are using hydrometer or pipette analysis, that I will discuss later. That is the for the soil which is passing 75 micron, that is the size less than 75 micron, we are usually doing hydrometer analysis or pipette analysis, and for other sand fraction and gravel fraction we are doing sieve analysis. Okay. Okay, so for this sieve analysis, I have told that we are collecting or we are calculating the weight of the soil which is collected or which is retained on each of the sieve. Okay, so after that we are calculating percentage retained on a particular sieve. So the percentage of the soil fraction which is retained on a particular sieve is equal to weight of the soil retained on that sieve divided by total weight of the soil into 100. So that is the percentage retained on a particular sieve. Okay. Next, after that we are calculating cumulative percentage retained. So cumulative percentage retained means it is a sum of percentage retained on all the sieves of the larger sizes. That is, there will be so many sieves. Okay, so we are calculating percentage sieve retained on each of these sieves, and cumulative percentage weight retained means that is for this particular sieve, if we are calculating cumulative percentage weight, we are adding this one, that is percentage weight retained here plus percentage weight here retained here plus here plus here. That is up to that sieve we are adding all the percentage of soil fraction which is retained. Okay, this will be clear after doing one problem. So now you just remember this equation, that is cumulative percentage weight retained is sum of percentage retained on all sieves of the larger size and the particular sieve, and percentage finer than the sieve means 100 minus cumulative. Okay, so first we are calculating percentage retained on a particular sieve by this equation, then cumulative percentage weight is calculated, then percentage finer means 100 minus cumulative percentage retained. So this is the analysis or calculation after the sieve analysis. Okay, and the results of the mechanical analysis plotted on a semi-log plot to get the grain size distribution curve. with a percentage finer on y-axis. So this is percentage finer. We have calculated percentage finer. So this percentage finer is plotted on the y-axis, and on the x-axis the grain size or particle diameter. Okay, that is on x-axis we are plotting the grain size or particle diameter, and on y-axis we are plotting the percentage finer. And that curve, after plotting this much, we will get what grain size distribution curve, and this curve gives an idea about the type and gradation of the soil. So this is grain size distribution curve. So on the y-axis we are plotting percentage finer, okay, or percentage passing, and on x-axis the particle size is plotted, and it is semi-logarithmic graph. Okay, so this is natural scale and it is logarithmic scale, so it is known as semi-log graph. So this is so in this grain size distribution curve, this is this plot is for this grain size distribution curve is for uniform soil, okay, and this is also for uniform soil S-shaped curve, and for cohesive soil this is the plot, that is particle size will be less than 75 micron, sorry 4.75, and this is for cohesionless soil. And there are some terminologies for this grain size distribution analysis. First is D10. Okay, D10 means D10 represents the size in mm such that 10% of the particle finer than this size. D10 means 10% is finer than that size, that is known as D10. And D30 means 30% of the particle is finer than that size. That is, for example, if so here this is D10, okay, that is D10 means in this y-axis we are taking the D10 value. So here it is D10 value, that means 10% is finer than this that size, that particular size. So here for corresponding 10 we are marking the value on x-axis. So x-axis we are getting a in x-axis we are getting a value corresponding to this 10, okay, and that is actually particle size. That is, for in x-axis there is particle size. So D10 means particle size. This is particle size such that 10% is finer than that particular size. And D30 means D30 will be here. So 30. We are extending this curve for this curve. For example, if we are taking this curve, D30 means draw a straight line corresponding this 30. So this is the point for 30% finer, and extrapolating this x-axis for here on x-axis we will get particle size around 0.12 like that. Okay, so here D30 is 0.12, that is 30% is finer than 0.12 mm. Okay, that is the meaning of D30. Like that, D10 means 10% is finer than that particular size. Like that, D60 means 60% particles are finer than that size. So these are terminologies D10, D30 and D60. And this D10 is also known as effective size or effective diameter. Okay. So this D10, D30 and D60 all are getting from this grain size distribution curve, and based on this or using this D10, D30 and D60 we are calculating uniformity coefficient and coefficient of curvature. So this is one of important parameter for coastal soil, that is uniformity coefficient Cu is equal to D60 by D10. D60 and D10, D30 extra we are taking from our grain size distribution curve, and uniformity coefficient Cu is equal to D60 by D10, and the coefficient of curvature Cc is equal to D30 square divided by D10 into D60. Okay, so this is also very important, you should by heart this one, what is uniformity coefficient, what is uniform coefficient of curvature. And based on this grain size distribution, we are categorizing the soil as well graded, poorly graded, uniformly graded and gap graded. Okay, so well graded means it means it is a good representation of grain size over a wide range, and its gradation curve is smooth. That is, in well graded there will be equal size of particle for equal weight. Okay, that is, the soil will be having all the sizes, that is, the soil mass will be having different sizes, and the fraction of each size will be equal. That is well graded. And poorly graded means if it has excess of certain particle and deficiency of other, that is, some particle size will be more, and some of the particle size is deficient. Okay, so that is, the particles are of same size, that is known as poorly graded. And uniformly graded means if the most of the particle are of same size, that is uniformly graded. Okay, gap graded means a curve with a hump, that is, there will be missing of one particular sieve size, so there will be gap, so that is known as gap graded. Okay, so well graded means there will be all the size particle, and all the size of the particle will be having same proportion, that is well graded. Okay, that is good representation of grain size over a wide range. That is, in well graded soil sample there will be all the sized particle with the same proportion, and in poorly graded there will be excess of certain particle and deficiency of certain particle, that is poorly graded. And in uniformly graded the particle size, that is, the most of the particle will be of same size, and in gap graded there will be missing of one particular sized particle. Okay, so this is the classification of soil based on grain size distribution. And for this for well graded, this coefficient of curvature is between 1 and 3. So coefficient of curvature means d60 d30 square by d60 into d10, that is cc is between 1 and 3 for well graded, and uniformity coefficient is greater than for gravel, greater than 4 for gravel, and greater than 6 for sand. Okay, so this is grain size distribution curve. Next is the use of grain size distribution curve, and this grain size distribution curve is used in the classification of coarse grained soil. Okay, and the approximate value of coefficient of permeability can also be determined from this particle size. If you know the particle size, we can calculate coefficient of permeability. So we will study coefficient of permeability in the next topic. Okay, and using this grain size distribution, we know susceptibility of soil to frost action. And using this one we can design the drainage filters. Usually these filters are designed based on size of the particle, and it will be obtaining using grain size distribution curve. Okay, and it provides an index to shear strength of the soil, that is, a well graded compacted sand will be having high strength. So if it is well graded soil means it will be having high strength, so we will get the shear strength using grain size distribution curve. And also the compressibility of the soil can be judged. A uniform soil is more compressible than well graded soil. Okay, so using this curve we can classify the soil as uniform soil or well graded soil, and a uniform soil will be more compressible than well graded soil. So like that we can judge the compressibility of a soil. And next use is useful in soil stabilization and for design of pavements. Okay, and it may indicate the age of residual soil deposit. With increasing age, the average particle size decreases because of weathering. Okay, so it is clear that is due to the passage of time there will be weathering, and due to weathering the particle size decreases. So actually it indicates the age of residual soil deposit. So these are the uses of grain size distribution curve. Okay, so this is sieve analysis. So the result of sieve analysis is plotted as a grain size distribution curve. So these are the important terminologies which are obtaining from this grain size distribution curve D10, D30 and D60. And using this there is uniformity coefficient Cu and coefficient of curvature Cc. And this is very important, that is the classification of soil from the grain size distribution curve, that is well graded soil, poorly graded, uniformly graded and gap graded soil. Okay, thank you.